is different. You are placing at the cutoff voltage your Q points, that's why your IC is equal to 0. For class C amplifiers, it is beyond your cutoff voltage. So some kind of reverse bias is provided in case of your class C amplifiers. In class AB amplifiers, this Q point is shifted near the cutoff voltage. These are the two main differences by which you can differentiate between these types of power amplifiers. This is class A amplifier, this is class B amplifier, class C amplifiers. These two main differences provide the difference between the power amplifier A, power amplifier B, power amplifier C and power amplifier AB. Now, collector efficiency for class A amplifier. When positive half cycle is at its peak, total collector current is equal to 2IC and the voltage VCE is equal to 0. When the negative half cycle is at its peak, the total collector current is equal to 0 and VCE is equal to 2 VCC. This can be shown in this output characteristics. Here we have considered two cases. This is your simple power amplifier circuit configuration. Here the output characteristics of the circuit. Here the Q point is at the middle of the load line. This is the DC load line, this is the AC load line. Again at y axis you are having the collector current, at the y axis you are having the voltage. Here you are providing the current configuration, here you are providing the voltage configuration. The two cases are when positive half cycle. So see, when there is the positive half cycle going, at this positive half cycle your IC is equal to 2IC. These are the values 2IC, IC 0, for voltage 0, VCC and 2 VCC. Considering two cases, when positive half cycle and when negative half cycle. For positive half cycle your collector current, this collector current is at maximum, that is 2 IC, but your voltage is 0. Similarly for negative half cycle it is vice versa, your voltage is maximum, that is 2 VCC, but the current is 0. Now coming to the derivation of this, peak to peak collector emitter voltage is VC peak to peak is equal to 2 VCC. Peak to peak, what do you mean by peak to peak? That is maximum value minus your minimum value. So in case of your peak to peak, VCE peak to peak, you are having V maximum minus V minimum. So in case of maximum it is VCC minus 0. So you are having 2 VCC, that we have derived here, that is 2 VCC. Again your PDC is, that is the DC power supply, that is the input to your power amplifier circuit. It is VCC into IC. Now PAC is VCE into peak to peak into IC peak to peak. We have the values of VCE peak to peak, that is 2 VCC, and IC peak to peak, that is 2 IC. Substituting these values you are having 2 VCC into 2 IC by 8. Now collector efficiency PAC upon PDC, you are having the value of PAC also and you are having the value of PDC also. We can substitute these two values here. PAC is your 2 VCC into 2 IC into 8 upon PDC, that is your VCC into IC. Now substituting these values we are having 50%, that is the collector efficiency of your class A power amplifier is 50%. This 50% is again a theoretical ideal value, but in practical it can be of 35% of maximum collector efficiency. Because of the power losses, coupling losses and transformer losses, this efficiency is reduced. Now comparison of amplifier classes that we have discussed here is in a simple tabular form we can discuss. For class A amplifier, operating cycle is 360 degree and the efficiency is 25 to 50%. For class B it is 180 degree operating cycle and efficiency is 78.5%. For class C amplifiers it is less than 180 degree the operating cycle and the efficiency is 75%. For class AB amplifiers the operating cycle is 180 degree to 360 degree and the efficiency is between 25% to 78.5%. Now the collector dissipation curve, we have discussed the power dissipation, that is the loss of energy in the form of heat. Now this dissipation curves defines or describes the operating limit of your circuit. This is the dissipation curve shown. Again you are having the two axes, x and y. The y axis shows the current and x axis shows the voltage. Here the region that is left to the collector dissipation curve is the region at which your circuit or component can work. If your operating point is to the right of this collector dissipation curve, it cannot operate, your circuit or component cannot operate. This collector dissipation curve specifies the operating limit of your circuit. When current flows through the collector of a transistor, some power is lost at the collector junction, and that is known as your collector dissipation. So this power is expressed as, we know that output it is Vc into Ic, where P total is the power lost at the collector junction. RMS value of collector emitter voltage is your VCE, and Ic is the RMS value of collector current. Since maximum power that a transistor can dissipate without overheating is constant, therefore your VCE dot Ic is constant. Now this Vc dot Ic is a hyperbola equation. If a curve is plotted as per equation on output characteristics of a transistor, a hyperbolic curve is obtained. So this hyperbola curve is called collector dissipation curve. The curve represents the actual operating region for the transistor. As we have discussed, the region left of the curve is operating region as marked, and the load line selected must lie below or to left of this curve, so that the operating limit is appropriate for the working of the component or the circuit. But if your current and voltage lies to the right of this curve, then the collector dissipation of transistor will exceed than the permissible limits. This will lead to the destruction of the transistor due to overheating. In simple words, we can define that your collector dissipation curves provides you the limit of the circuit, that if that particular limit is crossed, your transistor will go to the destruction. For the proper working of your transistor or the component of the circuit, it must lie in between the permissible limits. So the collector dissipation curve provides the permissible limits for your circuit for which it can operate. Now coming to the push-pull amplifier, as the name indicates, you are having transistors arranged in a form that one is pushing and one is pulling. Now why we have to go for a push-pull amplifier stage? In class A amplifiers we have discussed that it has very poor efficiency. You are having the linearity in case of our class A amplifiers, but the efficiency in case of your class A amplifiers were poor. But in class B amplifiers the efficiency was very good. Only the drawback was your distortion that occurred in case of your class B amplifiers. But for one particular cycle you are having the maximum efficiency. Therefore class B amplifiers which have higher efficiency are used at output stage in push-pull arrangement. We have provided two class B amplifiers in a push-pull arrangement in this push-pull amplifier. Why push-pull arrangement? Because during first half cycle one transistor is in conducting state, that is transistor for example 1 is pushing, that is in working stage, and other is in non-conducting state, that is it is pulling. Whereas in the second half cycle of the state of two transistors is reversed, that is transistor 1 in that particular point is non-conducting, that is pulling, and transistor 1 is pushing. In the circuit, no biasing is provided for two transistors because two transistors are to work in class B operation. We have discussed the class B power amplifiers. In case of class B amplifiers, your collector current was equal to 0. So no biasing circuit was provided in case of your class B amplifiers. In this operation, operating point is set at cutoff region for which no biasing is required. This is the circuit diagram for your class B push-pull amplifier. For push-pull arrangement we have discussed that we are using the class B amplifiers. So we are having two transistors that are placed in the class B arrangement. At the input you are having a driver transformer that is center damped. At the output also we are having a transformer coupling that is linked to the loudspeaker. The input signal is provided as an amplified signal at the output of the push-pull amplifier. The transistor T1 works for the positive half cycle, the transistor T2 works for the negative half cycle. Due to the center tapping at the output, you are having the complete amplified signal for both positive and the negative. A common battery is provided to both transistors T1 and T2. Now, it can be seen by the circuit arrangement that two transistors are placed back to back. As both transistors are operated in class B operation, that is collector current is 0 in the absence of the signal. The input signal is given to the circuit from driver stage to driver transformer, that is through primary secondary action transferred further. Secondary of the driver transformer is center tapped, which supplies equal and opposite voltage to the base circuits of two transistors. By designing proper turn ratio of the output transformer, suitable impedance matching is obtained to get maximum output across the road. You are employing again the transformer coupling. So, transformer coupling is employed for the impedance matching, that is maximum output can be obtained with respect to your input. During positive half cycle, as we have discussed, and A becomes positive and B negative, so transistor T1 is forward biased and T2 is reverse biased. Current will be conducted through transistor T1 only, and transistor T2 will be in cut-off state, that is pulling. Transistor T2 is in a pulling state and will not conduct any current. Therefore, first half cycle of the signal is amplified by transistor T1 and appears in the upper half of the primary of the output transformer. During negative half cycle, your operating limits are changed. Now your AND A becomes negative and B positive. This makes transistor reverse biased, transistor 1 reverse biased, that is now transistor 1 is in pulling state, and transistor 2 is forward biased, that is it is in a pushing state. Current will be conducted through transistor T2 only. Transistor 1 will be in cut-off state and will not conduct any current. Therefore, second half cycle of signal is amplified by transistor 2 and appears in lower half of primary of output transformer. The center tapped primary of output transformer combines the two halves of the cycle and forms a complete sine wave output in the secondary, that is positive half cycle amplified and negative half cycle combined and provided at the output. By proper impedance matching, maximum power can be transformed to the load. Now, coming to the advantages and disadvantages of this push-pull amplifier. The collector efficiency is high in case of your push-pull amplifier, as you are using the class B operation. Distortion free output is there, as complete one cycle positive half cycle is amplified by one transistor and another negative cycle is amplified by another cycle. More AC output power per device is achieved. Tendency of core to be saturated is eliminated, as both transistors are working vice versa to each other. Requires less ferromagnetic material, again the same reason that both transistors have the vice versa current configurations. The disadvantage: two identical transistors are required. In this case of your class B operation is required, you require the two transistors that are employed in push-pull amplifiers should be of identical specifications. That is very difficult. From one particular manufacturer you can take two transistors of same specifications, but in practicality even that same specification transistors will yield the different results that can affect your signal. Requires equal and opposite voltages at the input. You are having a common voltage provided for both transistors, and that at the input also you require that the signal that is given should be equal and opposite at the input. If the parameters of two transistors differ, there will be unequal amplification. As we are having the two transistors that should be identical, but in practicality the two transistors, even if they are from same manufacturer with same specifications, can yield different results. If they yield different results, it means you are having the unequal amplification. Unequal amplification means the distortion has occurred, and that is not desired. Now, coming to the complementary push-pull amplifier. The complementary push-pull amplifier is a little bit modification from your push-pull amplifier. As the name indicates, again push-pull arrangement is there, class B operation is there. You are using two amplifiers, one is pushing and one is pulling. The difference is that now the two amplifiers transistors that are working as amplifiers here are complementary to each other. That is, if one is NPN, another is PNP. If one is PNP, another is NPN. They are complementary to each other. In push-pull amplifier, two center type transformers are required, one at the input and one at the output. But in this complementary, no center type is employed, the center type is nullified. The complementary push-pull amplifier works on same principle of your push-pull amplifier. The two transistor used is one NPN and another NPN, that is complementary with symmetrical results. Here is the circuit arrangement of your complementary push-pull amplifier. So here you are having two amplifier stages, two transistor working as amplifier stages. The difference is that you are having the complementary. They are of symmetrical characteristics but complementary. Here you are having NPN, here you are having PNP. Center tapping is removed. The difference is that output transformer is there, but your battery potential is divided into two. If there was 12 volt a single to both the transistors, here you are having 6 volt and 6 volt to both the transistors individually. Center tapping is removed. Output transformer is employed for impedance matching to get maximum output across the load. The input signal appears across the terminal AB. During positive half cycle input signal, transistor T1 conducts while T2 not, as we have discussed in push-pull amplifier. Same principle has to be followed in this, but only difference is that the two transistors are complementary. During negative half cycle input signal, transistor T2 conducts and trier does not conduct. It is in cutoff stage. Hence, transistor T1 and PN amplifies positive half cycle and transistor T2, that is PNP, amplifies negative half cycle. The amplified signal appears across the primary, which is transferred to secondary or the load. So the advantages is center trap transformer is not required, weight and cost is less, and the efficiency is high in case of your complementary push-pull amplifier. Center type transformer is not required here, so your weight is less as compared to your push-pull amplifier. The disadvantage is that it is very difficult to get pair of transistors having same characteristics. In case of your push-pull amplifier, we discussed that we need two identical transistors. There we needed two identical transistors, that is both should have be PNP. Here we need one NPN and one PNP. So the chances of your irregular amplification is increased in case of your complementary push-pull amplifier, as we need two complementary transistors of symmetrical characteristics, that is difficult to achieve. Again, the second disadvantage is required two batteries of half the voltages. In case of your push-pull amplifier, you needed only one battery. Here you required two batteries of half the voltages. So we can sum up your whole lecture here. The power amplifier was the last stage that was used in your amplifier stages. First few stages were your voltage amplifier. In multi-stage amplifiers, the first few stages are your voltage amplifiers that raise the particular signal strength of the signal. Then it is given to a driver stage that simply interconnect your output to the last output circuit. Before the output circuit, you are having a power amplifier stage. Now that power amplifier stage is discussed here in this lecture. That power amplifier stage provides maximum output power so that it can drive your circuit. I hope you understood the lecture. Thank you very much.